Augmented reality is a live, direct or indirect view of a physical, real-world environment whose elements are augmented by computer-generated sensory input such as sound, video, graphics or GPS data. It is related to a more general concept called mediated reality, in which a view of reality is modified by a computer. As a result, the technology functions by enhancing one's current perception of reality. By contrast, virtual reality replaces the real world with a simulated one. Augmentation is conventionally in real time and in semantic context with environmental elements such as sports scores on TV during a match. With the help of advanced AR technology, the information about the surrounding real world of the user becomes interactive and digitally manipulable. Information about the environment and its objects is overlaid on the real world. This information can be virtual or real, e.g., seeing other real sense-to-measured information such as electromagnetic radio waves overlaid in exact alignment with where they actually are in space. Technology. Hardware components for augmented reality are processor, display, sensors and input devices. Modern mobile computing devices like smartphones and tablet computers contain these elements, which often include a camera and MEMS sensors such as accelerometer, GPS and solid-state compass, making them suitable AR platforms. Display. Various technologies are used in augmented reality rendering, including optical projection systems, monitors, handheld devices, and display systems worn on the human body. Head-mounted. A head-mounted display is a display device paired to the forehead such as a harness or helmet. HMDs place images of both the physical world and virtual objects over the user's field of view. Modern HMDs often employ sensors for 6 degrees of freedom monitoring that allow the system to align virtual information to the physical world and adjust accordingly with the user's head movements. HMDs can provide users immersive mobile and collaborative AR experiences. In January 2015, Meta launched a $1 project led by Horizons Ventures, Tim Draper, Alexis Ohanian, Bo Optoelectronics and Gary Tan. On February 17, 2016, Meta announced the second-generation product at TED, Meta 2. The Meta 2 head-mounted display headset uses a sensory array for hand interactions and positional tracking, visual field view of 90 degrees, and resolution display of 2560 by 1440, which is considered the largest field view currently available. Eyeglasses AR displays can be rendered on devices resembling eyeglasses. Versions include eyewear that employ cameras to intercept the real-world view and redisplay its augmented view through the eyepieces and devices, in which the AR imagery is projected through or reflected off the surfaces of the eyewear lens pieces. Hard near-eye augmented reality devices can be used as portable head-up displays, as they can show data, information, and images while the user views the real world. Many definitions of augmented reality only define it as overlaying the information. This is basically what a head-up display does. However, practically speaking, augmented reality is expected to include tracking between the superimposed information, data, and images and some portion of the real world. CrowdOptic, an existing app for smartphones, applies algorithms and triangulation techniques to photo metadata, including GPS position, compass heading, and a timestamp to arrive at a relative significance value for photo objects. CrowdOptic technology can be used by Google Glass users to learn where to look at a given point in time. In January 2015, Microsoft introduced HoloLens, which is an independent smart glasses unit. Brian Blau, Research Director of Consumer Technology and Markets at Gartner, said that, "Out of all the head-mounted displays that I've tried in the past couple of decades, the HoloLens was the best in its class." First impressions and opinions have been generally that HoloLens is a superior device to the Google Glass, and manages to do several things right, in which Glass failed. Contact lenses that display our imaging are in development. These bionic contact lenses might contain the elements for display embedded into the lens, including integrated circuitry, LEDs and an antenna for wireless communication. The first contact lens display was reported in 1999 and subsequently, 11 years later in 2010-2011, another version of contact lenses, in development for the U.S. military, is designed to function with our spectacles, allowing soldiers to focus on close-to-the-eye images on the spectacles and distant real-world objects at the same time. The futuristic short film site features contact lens-like augmented reality devices. Virtual retinal display. A virtual retinal display is a personal display device under development at the University of Washington's Human Interface Technology Laboratory. With this technology, a display is scanned directly onto the retina of a viewer's eye. The viewer sees what appears to be a conventional display floating in space in front of them. iTap. The iTap captures rays of light that would otherwise pass through the center of a lens of an eye of the wearer, and substitutes synthetic computer-controlled light for each ray of real light. The Generation 4 glass is similar to the VRD, except that it also has infinite depth of focus and causes the eye itself to, in effect, function as both a camera and a display, by way of exact alignment with the eye, and resynthesis of rays of light entering the eye. Handheld displays employ a small display that fits in a user's hand. All handheld are solutions to date opt for video see-through. Initially handheld are employed for visual markers, and later GPS units and MEMS sensors such as digital compasses and 6 degrees of freedom accelerometer gyroscope. Today SLAM markerless trackers such as PTAM are starting to come into use. Handheld display are promises to be the first commercial success for our technologies. The two main advantages of handheld is the portable nature of handheld devices and ubiquitous nature of camera phones. The disadvantages of the physical constraints of the user having to hold the handheld device out in front of them at all times, as well as distorting effect of classically wide-angled mobile phone cameras when compared to the real world as viewed through the eye. Spatial augmented reality augments real-world objects and scenes without the use of special displays such as monitors. Head-mounted displays are handheld devices. SAR makes use of digital projectors to display graphical information onto physical objects. The key difference in SAR is that the display is separated from the users of the system. Because the displays are not associated with each user, SAR scales naturally up to groups of users, thus allowing for collocated collaboration between users. Examples include shader lamps, mobile projectors, virtual tables, and smart projectors. Shader lamps mimic and augment reality by projecting imagery onto neutral objects, providing the opportunity to enhance the object's appearance with materials of a simple unit: a projector, camera, and sensor. Other applications include table and wall projections. One innovation, the extended virtual table, separates the virtual from the real by including beam splitter mirrors attached to the ceiling at an adjustable angle. Virtual showcases, which employ beam splitter mirrors together with multiple graphics displays, provide an interactive means of simultaneously engaging with the virtual and the real. Many more implementations and configurations make spatial augmented reality display an increasingly attractive interactive alternative. A SAR system can display on any number of surfaces of an indoor setting at once. SAR supports both a graphical visualization and passive haptic sensation for the end users. Users are able to touch physical objects in a process that provides passive haptic sensation. Tracking. Modern mobile augmented reality systems use one or more of the following tracking technologies: digital cameras and/or other optical sensors, accelerometers, GPS gyroscopes, solid-state compasses, RFID and wireless sensors. These technologies offer varying levels of accuracy and precision. Most important is the position and orientation of the user's head. Tracking the user's hand or a handheld input device can provide a 6DoF interaction technique. Input devices. Techniques include speech recognition systems that translate a user's spoken words into computer instructions, and gesture recognition systems that can interpret a user's body movements by visual detection from sensors embedded in a peripheral device such as a wand, stylus, pointer, glove or other bodywear. Some of the products which are trying to serve as a controller of our headsets include Wave by Seabright Inc. and Nimble by Intugene Technologies. The computer analyzes the sensed visual and other data to synthesize and position augmentations. Software and algorithms. A key measure of VAR systems is how realistically they integrate augmentations with the real world. The software must derive real-world coordinates independent from the camera from camera images. The process is called image registration, which uses different methods of computer vision, mostly related to video tracking. Many computer vision methods of augmented reality are inherited from visual odometry. Usually those methods consist of two parts. First, detect interest points, or fiducial markers, or optical flow in the camera images. First stage can use feature detection methods like corner detection, blob detection, edge detection of thresholding and/or other image processing methods. The second stage restores a real-world coordinate system from the data obtained in the first stage. Some methods assume objects with known geometry present in the scene. In some of those cases, the scene 3D structure should be pre-calculated beforehand. If part of the scene is unknown, simultaneous localization and mapping can map relative positions. If no information about scene geometry is available, structure from motion methods like bundle adjustment are used. Mathematical methods used in the second stage include projective geometry, geometric algebra, rotation representation with exponential map, Kalman and particle filters, nonlinear optimization, robust statistics. Augmented reality markup language is a data standard developed within the Open Geospatial Consortium, which consists of an XML grammar to describe the location and appearance of virtual objects in the scene, as well as ECMA script bindings to allow dynamic access to properties of virtual objects. To enable rapid development of augmented reality application, some software development kits have emerged. A few SDKs such as Cloud.It leverage cloud computing for performance improvement. Some of the well-known R SDKs are offered by Vuforia, RToolkit, Catum Crafter, Mobinet, Wikitude, Blipper Layer, Meta.